You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you.
Hello, this is Richard Jacobs with the Future Tech and Future Tech Health Podcast. I have Professor Jacopo Buongiorno. He's part of the nuclear engineering department at MIT. We're going to be talking about artificial blubber that they're creating to keep Navy SEALs warm, which sounds really interesting. So, Jacopo, thank you for coming.
Yeah, my pleasure. Thank you for inviting me.
So, I guess, I don't know, is the human body not very resistant to water temperature with conventional wetsuits? Like, what's the need for this?
Yeah, it absolutely depends on the temperature of the water one jumps in, as I think we've all experienced, that particular certain latitudes. If you stay in cold water for too long, then your body starts to feel numb. And if you really stay in there for too long, then you go into what in medical terms is called hypothermia, and that can ultimately kill you. So particularly for applications either defense related or even recreational, if one wants to stay in cold water for long periods of time, traditional wetsuits are probably not sort of a good option.
Yeah, I don't know much about them, but I thought wetsuits were designed to keep the cold out. Like how if I was in cold water, cold meaning, I don't know, 50 degrees Fahrenheit, without a wetsuit versus with one, how much longer would I last with a conventional wetsuit?
So conventional wetsuits do provide a certain amount of thermal insulation, so you're going to be much better off with a wetsuit, any wetsuit, than being sort of bare in the water for sure. But you're still, once again, depends on how cold the water is, but let's say freezing water, literally in, polar environment, you probably wouldn't last, without a wetsuit, probably minutes, and with a wetsuit. Conventional wetsuit, maybe 20 or 30 minutes. In fact, these numbers have been published, and we include them in our publication. And our goal from the beginning was to see if we could extend for a given water temperature, a given low water temperature, the time to hypothermia by a factor of 2 or 3. And we think we found a way to do that.
So were you studying whales or dolphins, or what kind of animals were you studying to look at their blubber?
Yeah, it's interesting you asked me that question, because in fact the initial impetus or initial inspiration for our work did come from animals that normally live and operate, so to speak, in very cold waters. And so there are essentially 3 approaches that animals use to protect themselves from frigid waters. The first is blubber. That's for seals and the like. Essentially, blubber is a thick layer of fat matter that has a fairly low thermal conductivity, or if you wish, a high thermal resistance. And the thicker it is, the more insulating that blubber is. So that's the first approach. A second approach, which is used, for example, by otters, is to have a very thick coat of hair. And it's so thick, and it is designed in a certain way that it actually traps some air in it, and it's the air within the hair coat that basically provides insulation. Because air is a gas, and as such does not have a very high conductivity for heat, so it insulates the body. And then the third approach is for warm-blooded animals such as orcas or even great white sharks. The body actually generates heat at a much higher rate than other animals, and by generating heat internally, they're able to keep the body temperature at a higher level. So we initially look at all these different strategies, and we decided to focus on some technology that would mimic these three different strategies.
Well, I guess there'd be a bunch of trade-offs, like, you couldn't have a very furry suit because that would probably trap tons of water and weigh the person down. So blubber seems like, in a water environment, probably the best solution.
Yeah, and so we indeed start with an artificial blubber, and you're absolutely correct. There are trade-offs. There are limits. One cannot simply don a wetsuit that is 3 centimeters or 2 inches, say, thick, because then your movements would be impaired, right? For example. And so our goal was to design a wetsuit that would effectively feel the same way in terms of a dynamic interaction with the body. The way it would allow you to swim in the water would feel like a traditional wetsuit, say 5 or 7 millimeter thick, but it would have a far superior thermal insulation property. And so the way in which we accomplished that was by replacing a gas that is normally present in neoprene. Neoprene is the material that wetsuits are made of, with a gas that has a lower thermal conductivity. And we're able to show that the resulting material as a much better insulation than traditional wetsuit, than traditional neoprene, and therefore traditional wetsuits.
Do you have like an air gap layer and then the blubber begins, or how's it structured?
So we don't have an air gap. There are some air gaps that naturally develop between the body and a wetsuit. That's almost, I would say, independent of the material the wetsuit is made of. It's just that the fit of a wetsuit might not be perfect, and so you do have some air gaps present. Those air gaps actually theoretically would help with the insulation because, again, air is a good insulating gas. But we're not relying on those air gaps to provide insulation. We've actually introduced an insulating gas within the neoprene material itself. So let me maybe take a step back and describe what neoprene is. Neoprene is rubber, and in the form that it's used in wetsuits, it's sort of a foamed rubber. So in other words, you have, think about Swiss cheese, right? So you have rubber, but you have lots of pores or lots of holes. And the insulating property of a wetsuit or a neoprene comes partially from the fact that neoprene itself, the material, the rubber, is low thermal conductivity, but perhaps more importantly by the fact that you have all these air trapped within the material itself. Now, we studied the way in which heat is transferred across this material, and we found that roughly half of the heat transfer actually occurs through the gas itself. And so it matters which gas you have in there. And so the initial idea for our technology is very simple. Instead of using nitrogen and air, which is the gas that you would find within traditional neoprene, we have replaced that with lower thermal conductivity gases such as xenon or argon and krypton. And so those are heavier gases, and as such, they tend to conduct heat less well, which is good news in this case because you're trying to insulate the body.
What about the porosity as you go from in to out? Would it help to have it highly porous on the innermost side of it and then less porous as you go out towards the water side? I mean, are there any advantages to structuring it like that?
So that's not how wetsuits are typically designed. They have the neoprene for traditional wetsuits is essentially as a porosity distribution, which is uniform. The pores are everywhere and they're more or less the same. But your idea is a good one. One, for example, could think of smaller pores on the outside to prevent essentially the gas that you've introduced as your insulating gas to leak out very easily. And in fact, that's what we are sort of tackling now in research spaces, we have shown conclusively through both, coupon samples as well as full treated wetsuits that indeed our idea works. In other words, it reduces the effective thermal conductivity, or if you wish, it increases the thermal insulation of the wetsuit. But what we have not been able to show is that once we treat the wetsuit with that new gas, that gas stays in for long periods of time. And so, in fact, we see that it leaks out over, depending on the gas and depending on the neoprene that we use to begin with, the gas might leak out over a period of, say, 24 hours, 48 hours. The process is reversible, which is interesting. So if we retreat it, we regain the good properties that we want. But you can appreciate from a practical point of view, there are some applications in which these regular retreatment of the wetsuit would not be a big deal. But for example, if you are a recreational surfer or a diver, you would have to retreat your wetsuit every time. That may not be very convenient. So we're now focusing on how do we create a barrier for that gas that would keep the gas in and therefore make our effect permanent, if that makes sense.
Yeah, no, it makes sense. Does the gas tend to migrate out, or does it tend to migrate in?
Yeah, so in the tests that we do, it tends to migrate both ways because essentially we have an open environment on both sides. But not surprisingly, if you have, for example, water on one side, which tends to have a low diffusion coefficient for gas, and you have open air on the other side, then it will migrate primarily towards the open air side, just because it's it's the path of least resistance for the gas to leak out. And so I think it's going to boil down to creating some kind of a barrier, either on the surface of the material or preferably even within each individual pore, so that when those pores are charged with that new gas, basically the gas stays in. But that it makes for an interesting research project now.
Well, yeah. What have you learned about studying the blubber of various animals? Are there certain ones that have better blubber than others, or is there a variation in the thermal properties of blubber of an orca versus a dolphin?
Yeah. There is those variations are minimal because they all use the same material, which is animal fat. Effectively, that's what blubber is made of. In our material has an effective thermal conductivity or insulation that is far superior to natural blubber. So our comparison, our thermal comparison, so to speak, is not animal blubber. That was the initial inspiration, but our material actually has a much lower thermal conductivity already. So, in fact, it's interesting. In some extreme cases, we can get an effective thermal conductivity of the treated neoprene, which is equivalent to the thermal conductivity of air. So it's almost like you're wearing a garment made of air, right? So it's an interesting way to look at it. It's not really made of air. It's made of It's made of a composite material that has a thermal conductivity of air. So very, very low, that is.
With animals, though, I mean, I guess that they don't obviously have to recharge their blubber, or I don't know. Maybe they do. Maybe gas is migrating into the blubber somehow. What else is there to be learned from studying animals, or do you feel like from here it's going to be more of an engineering problem?
No, there is still a lot to be learned from Mother Nature. Evolution works over very long periods of time, and through just sort of random testing of combinations, it does select the best design possible, at least for the environment in which it takes place. So, bottom line, there is a lot to be learned from nature. I mentioned at the beginning that there are animals that do not rely on blubber, but they do rely on a thick coat of hair. Otters is one that comes to mind. Polar bears also use this, and so we're trying actually now to combine the two approaches. So the artificial blubber that we've just been discussing for the past 10 minutes, with some kind of synthetic coat that would trap some air and basically give you additional insulation. The synthetic hair can also be engineered to reduce the drag, associated with the body, and so in addition to having insulating benefits, you might also be able to swim faster for a given amount of effort. And so we're looking at that, but we don't yet have conclusive results on that particular idea that I'm able to discuss now. Right now, it's just sort of research.
Is there, I don't know, what if you were able to direct the escape? Let's say there was two layers and the gas would preferentially escape towards the center. Maybe there would be a channel in the center that would migrate the gas around to where it was deficient, needed. Maybe that would be a mechanism to keep it there longer.
Yeah, there are all sorts of, possible creative ideas, but we're really trying to keep things simple, practical, and low cost. Again, we have a portfolio of applications in mind from defense, from Navy SEALs. Incidentally, I should say that a treated wetsuit was recently tested in a Navy trial back in I think in May here in New England. So in cold water. I mean, not obviously freezing water, but pretty cold. And qualitatively, the divers saw that that our wetsuit was warmer than what they were used to. But that's one application is, say, Navy SEALs, because they tend to spend a lot of time in water, and that water is not always nice and toasty. But I mentioned, recreational divers, surfers, triathletes, shipyard workers, that, also all these categories, people that would use wetsuits as part of their activities. And you really need to keep things simple, manageable, and relatively cheap. Otherwise, you're not going to have a market. So we're trying to really strive for that.
In a normal wetsuit, what percentage of the outermost part of the wetsuit gets wet? Like, how deep does it saturate in? And is there anything to be gained there by, having less of the suit saturate?
Yeah, there is. So the pores are relatively small. We're looking at things like hundreds of microns. Nonetheless, depending on the material, the neoprene itself, whether the material is laminated with a sheet of nylon or nylon-like material, you can have, as you just mentioned, penetration of water inside the pores. Of course, that's detrimental to the performance of the wetsuit. And so to the extent that you can engineer the inside of the pores to be essentially hydrophobic, you might avoid that. I think the way it's typically done is they put a foil, or I call it a sheet of some plastic or some polymeric material on the outer surface that prevents water from coming in. On the inside, the reason why it's called a wetsuit is because basically it's not a sealed tight garment, and so you allow for a thin film of water to penetrate between the skin and the wetsuit. And what's key there is to make sure that water stays stagnant, that it doesn't flow in and out of the wetsuit, because otherwise you get very cold very fast, right? But generally speaking, yes, keeping water out of the material, out of the wetsuit material itself, is certainly a worthy design goal.
And what about, on a person's body? I mean, from what I know, the head and the feet are the two greatest areas where heat gets exhausted. I mean, in terms of making the suit, can you preferentially engineer it so that the areas that leak the fastest will leak the slowest or be the most insulated?
Yeah, you could. And by the way, this gives me an opportunity to say that it's not just the wetsuit. We are also looking at treating neoprene gloves or caps or booties and so on. So I mean, it's the whole body has to be protected. But you're absolutely right. Certain areas of the body tend to leak more energy or more heat out, or lose more heat than others. And it really depends on the on the proximity of the blood vessels to the surface. And so the head, the neck, and so on, they tend to have a lot of blood vessels close to the surface. So the surface is warmer, which causes more heat loss. And so you would want to protect there preferentially. And so again, with traditional wetsuits, you're somewhat limited, because the way to protect it with a fixed material would be to just increase the thickness of the material in that region. But if you think about for example, the neck area, the shoulder area, and you're a swimmer, you want to make sure that your body moves freely or anyway easily because you're swimming. And if you're wearing a wetsuit that is very thick in those areas, that limits your motion. So with our idea, you would be able to maintain a thin wetsuit so that it doesn't impair motion, and at the same time have an acceptable thermal insulation in those areas.
Well, when you were talking about otters and animals with a thick layer of hair, like at least for me, luckily I still have my hair, but I guess part of the suit, maybe you can make a hat portion that uses the thick hair on the head and makes it very, very insulating with rubber hat in addition to the rest of the wetsuit. And then what if you were to make a back panel that was like super insulating? So at least when the person gets colder, there's still a reserve of warmer part of the body that can flow to the colder part and maybe keep it going longer. Maybe by preferentially making it thick in the areas where it can be thick and it won't impede you, that it will help keep you warmer longer.
Yeah. Again, all good ideas. Along that line of thinking, we are studying first of all, where the most of the heat losses take place, number one. But number two, also, where most of the drag comes from if you are a diver, an underwater swimmer. And not all areas of the body contribute to drag the same way. And if you can identify which area contribute the most, then you can put some drag-reducing hair the same way that otters have it in those regions. And so it's not a simple problem. It actually entails really studying the details of how water flows around the human body in certain positions. And we discover as part of this project that there is not a very big literature out there on this. There is actually more literature on this for surface swimmers because I think it helps them improve in sports like the Olympic swimming and so on. Not as much in underwater swimmers or divers, if you wish. And so we're now basically studying that problem using computational fluid dynamics, and it's quite interesting to see which areas of the body sort of give you the most drag. I'm not ready to tell you which areas there are because we're analyzing the data right now, or the results of the calculations.
Is there any assist with the pressure as you go down? Or is that detrimental to the thermal insulation?
Yeah, it is actually detrimental, and that's I'm glad you brought it up. It's detrimental because as you go deeper, the hydrostatic pressure of the water surrounding you, of course, goes up, and that tends to compress the pores, and so effectively you're going to have a lower porosity in your neoprene, and that increases thermal conductivity, so your heat losses go up. This is well known also with traditional wetsuit materials, and so we're studying ways to effectively buttress, if you wish, or strengthen the pores themselves, so that even as you dive deeper and deeper, the porosity stays the same, and therefore your insulation stays the same.
Yeah, it's a very challenging problem. A lot of interesting stuff. What fresh water versus salt water? I mean, I guess most of the diving happens in salt water, or most of the activity. I don't know, any differences there, or that's not really material to what you're doing?
No major insight I can give you there. The dominant thermal resistance to heat loss, if you wish, in the system is indeed the wetsuit. So in a way, the type of fluid that you have on the outside almost doesn't make much of a difference, whether it's water or fresh water, or salt water. And it might end up having a significant effect potentially on the durability of whatever coating you put on the outer surface, or to protect or to create a barrier for the gas leak, or even if you end up coating the parts or regions of the wetsuit with synthetic hair, it might have an effect on the durability of that hair. But we're not there yet. We haven't studied the differences between fresh water and salt water yet.
Is it possible to put any electric potential or any to help make it work better?
Yeah. So we should have mentioned from the beginning that this is a collaboration between two research groups here at MIT, my own and Professor Michael Strano's. in Department of Chemical Engineering. And so Michael eventually might want to tell you more about his technology, but he has developed what he calls Thermo Resonators. Essentially, these are small devices that harvest energy and exploit temperature fluctuations that are naturally present in the environment to, for example, charge a battery. So they turn some heat into electricity, and they charge a battery, and then you could use those batteries to apply a heat flux or to generate some heat to basically keep the body warm when you need it. And so this, in a way, would be mimicking that third strategy that we see in nature, in animals, the warm-blooded animals that generate more heat internally to keep their body temperature high.
Okay, interesting. Well, very good. What do you expect will be some milestones for your group in the next 6 months or a year?
Yeah, so we have connected with a Navy lab here in Massachusetts that does testing of wetsuits, gloves, caps, booties, the whole set of garments that Navy divers use for their dives, and we will be starting, I think, next week or the following week, testing, sort of a very systematic testing of different materials that we've been developing in that lab, and hopefully this will confirm not just on coupon samples and not just qualitatively with divers, but with an actual control setting in a lab that these different garments will have a better insulation property. They basically, in this lab, they use mannequins and they're able to measure the heat losses at different locations on the human body under different conditions, say different water temperatures, and of course with different materials for the garment itself. So we are excited about that. It gives us an opportunity to strengthen our relationship to the with the Navy. I should also mention the project has been sponsored by the Neptune program, which is a Office of Naval Research program, and we're excited to see if in fact these garments do provide a significant better insulation. Then ultimately we can deploy them in the field.
That's great. And how can people find out more? Can they get in touch with the lab, or perhaps you? It's up to you.
We're very easy to find. Just go to mit.edu, type in either my name or Michael Strano's name, and you'll find our contact information. We're very happy to take questions, suggestions, comments anytime. And if somebody's really, really interested, we might even invite them over to our lab and show them the treated wetsuits and how we measure things, and have an interesting, exciting discussion about this research project.
Well, great. Well, Jacopo, thank you so much for coming. I appreciate it.
Yeah, it's been really my pleasure. Thank you for inviting me.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.